Now let's look at the estimation part. Let's say some parameter estimation. I want to estimate the mean of a population, or I want to estimate the variance of a population. See, in our central limit theorem, what we have said is probably the sample mean is an estimator to the population mean, and it's a normal distribution with variance equal to sigma squared by n kind of stuff. Now, when I have to do any estimation, given some data, let's say a raw data is given, that too not 30 plus elements or something, where I can directly use the central limit theorem and all. If at all I just have around 10 data points, and at the same time I have an idea about the distribution which that particular values can follow. Based on that, I can try to estimate the mean or the variance by looking at the sample observations. So from that standpoint, we have two different modes of estimation. One is a point where we are estimating only one value, whereas the other one is an interval. The next chapter deals with an interval based estimation, which is a confidence interval estimation. Whereas initially, when I start off with the point estimation, it is more to estimate one value, a pointed value to a particular parameter. So there are again 2-3 methods to estimate that, right? So finding a single number estimate to a parameter value is what is our intention. So we will talk about the two major methods to do that. One is called as the method of movements. Movements are nothing but finding out the mean, the variance from the skewness and all from the data. They are all the typical movements. So we are using that method of movement to estimate the unknown parameters. And the second one is the method of maximum likelihood. We use the concept of differentiation heavily here to estimate the parameter based on the maximum likelihood. Probably the better and effective way of estimating the parameter is the maximum likelihood kind of estimation. Even it has a lot of applications in the real world also, and probably from your exam standpoint also, the questions can very comfortably be expected on the maximum likelihood based estimation. Now, what do we talk, what do we say when we have to talk about the method of movements? It is nothing but, see here, these kind of things are applicable for estimating parameters. See, in our in every distribution there are some parameters, right? For example, in a binomial distribution we have n, p, some values which are to be known, right? In our Poisson distribution there is a lambda. In exponential distribution, again there is a lambda. So each of the distribution, and in gamma distribution there are two, alpha and lambda. So these are what we are calling as parameters. And how do I estimate these parameters from the data, right? Because at the end, if I have to associate that this will follow a normal distribution or this will follow an exponential distribution, unless I know those parameters, it's not easy for me to draw a probability distribution or find out the integrations or find out the areas or whatever are there. So from that standpoint, this method of movements is typically being used. In this case, if it is a method of movements kind of a estimation, the process is very simple. You find out the sample moment and solve it for the parameters of the population. It's as good as, let's say, if the question is like this: a random sample from an exponential distribution. So these are the values of exponential distribution. right? Some probably you have the intention that the claims follow an exponential distribution or something like that. So let's say these are the values which are generated out of the exponential distribution. Based on this, we know that the exponential distribution has a parameter, has a probability function of lambda e power minus lambda x. So if at all the values are like this, he is asking us to find out the value of lambda. What could be the value of lambda if the sample observations are more like this? So in these cases, few things we can understand is, for an exponential distribution, the sample mean, the mean is actually equal to 1 by lambda. For an exponential distribution, the mean is 1 by lambda. So what I can do, I can find the mean of these values and equate it to 1 by lambda. That is what is the method of moments estimate, which is you find out the mean of the sample. You know the mean of the exponential distribution, what is the formula? Equate the two, and from that you obtain the value of your lambda. So it is more like, now if the numbers for us, (14.84, 0.89, 11.75, 1.18, 2.44 and 0.53. I think 0.19, right? Okay. So what we are saying is, let's say I have only this 6 data, right? With this 6 data, I want to fit this data into an exponential distribution. So for an exponential distribution, the only thing I need is lambda. And we also know that the mean of an exponential distribution is 1 by lambda, right? And the mean of this, I can find out the mean of this data, which is the average of this, is equal to 5.155. So 1 by lambda equal to 5.155. So based on this, I can get lambda, which comes out to this much. Lambda is 1 by 5.155, so which is 0.1939. So using this data, if I want to find out, see from here what he says, you estimate the lambda and probably use this for what is the probability that an average, the average claim is greater than 10, right? See, the way the question goes is, a sample of data will be given and asks us to estimate the parameter called lambda. Use that parameter lambda to find out the probability that average claim size, or whatever is that number, average that the number is greater than 10. So how do I use that now? Now if I get my lambda as 0.1939, or probably if I round off 0.194, that is what is the lambda we got. So if the question is greater than 10, right? So what is that we are saying? What is the probability of greater than 10? So it is nothing but 10 to infinite, right? For an exponential distribution, if the question goes extended like that, the way we are solving is lambda e power minus lambda x dx. So it is becoming lambda, the integration of e power minus lambda x is e power minus lambda x by minus lambda. This is getting integrated between infinite and 10. So minus of e power minus infinity is 0. minus e power minus 10 lambda. So the probability is coming out as e power minus 10 lambda. Now we know the lambda, right? Minus 10 into lambda is 0.194. So we are saying this is equal to e power minus 1.94. So what is that? It is resorting to. So we are saying e power minus 1.94. So it is saying there is a 14.37% chance. There is a 14.37% chance that just by looking at this 6 data, right, and assuming that these are coming from an exponential distribution, the probability that the value is greater than 10 is nothing but 14.37%. So that is how we use the method of moments kind of. So basically the intention of method of moments estimation is estimate the parameters. For any distribution, just find out the mean and the variance or whatever. See, some of them have only one parameter, like exponential distribution has only one parameter lambda. Poisson distribution has only one parameter lambda. Whereas the binomial distribution has two parameters, n and p. Or probably a gamma distribution has two parameters, alpha and lambda. So wherever there are two parameters, it is advised that you compute the mean and the variance, both of them, and equate them to the formulas. Right? Now let's look at the next one. So if there are two unknown parameters, we need two equations. Right? Look at the better this example, where we need to know both n and p. Both the estimates are required. See, we know that this is a sample coming from a binomial distribution. Right? This is a sample coming from a binomial distribution. Now I want to find out the values of n and p from here. So 4, 2, 7, 4, 1, 4, 5, 4. So 4, 2, 7, 4, 1, 4, 5, 4. These are the values. So we know that the mean in a binomial distribution is NP. Right? So the mean of this also I can find out. I can find out the mean of this and say NP equal to 3.875. Similarly, the variance of a binomial distribution is NP into 1 minus P. Probably I can find out the variance of this data also. The variance of this data, right? The mean, you can do the same. Each value minus the mean whole squared divided by n minus 1. Probably I'll do that part also. So the variance is coming out to 3.26. The way we got that variance was each value you subtract the mean. Each value you subtract the mean and then do a square. Each value subtracted the mean and did a square, and the sum of this divided by n minus 1, because it's a sample variance. For sample variance, you divide the sum of the squares of the difference, the squares of the sum of the squares of the differences, we divide by n minus 1. For a population variance, we divide it by n. So here we are saying the sum of all these things divided by 7. which is what is coming out to 3.2678. So your NP into 1 minus P is 3.26. So probably you can substitute NP here, right? So it comes out like 1 minus P is equal to NP into 1 minus P by NP, right? So which is nothing but this number divided by this number, right? This is 1 minus P, which is 0.84. So based on this, you will get P is 1 minus of this. So you know that the probability of success in this case is 15.66%. Whatever is the success, we are saying that the probability of success in this case is 0.1566 or 15.66%. Now you can substitute this back and find out your N. Your N is coming out as in NP, I will put that. So this by P. So my NP is coming out to some 24.73 and N is the number of trials, right? Number of trials or number of times an experiment is performed. It cannot be 24.73, so probably it should be rounded up very close to 25. So we will say 25 out of 25 times an experiment is repeated, right? The way we are saying is 25 times experiment is repeated. In some cases there were 4 successes, in some cases there were 2 successes, in some cases 7 successes and something like that. The number of successes when an experiment is repeated n times. So if it is following a binomial distribution, we are saying n should be 25 and p should be 0.15, 15.66%. Only in that case, so without knowing the probability of success, now if you try to understand, without knowing the probability of success, we are finding out the probability of success, right? Without even knowing how many trials have been performed. So based on whatever is the available data and an assumption of a distribution, see, generally what happens is some of the items, we assume that they follow some distribution, like claim amounts. We assume that it follows a kind of log normal kind of a distribution or exponential kind of a distribution. We have some kind of initial, based on the experience, we can come out that it follows this kind of a distribution. But from the existing data, I want to fit in what is the expected value associated with that, right? So if I have a 2 sample kind of a case, I'll do it something like this. And now once I know N and P, I can find out any probability. What is the probability of getting more than 20 successes, right? We don't have the 20 successes scenario at all here. But we can find out now the probability of getting 20 successes. If the question is saying what is the probability of 20 successes, you can very well say NC20, so 25C20 into P power 20, P we got, into 1 minus P to the power 5. It says very 0.00001% of getting more than 20 successes. So just from a small sample of data, just under the assumption that it follows a particular distribution, we can calculate any kind of probabilities if I am able to estimate the parameters, right? Look at one more here, the sample mean and the sample variance for a large random sample from a gamma distribution are 10 and 25 respectively. So again, if I am using the method of moments, the mean is alpha by lambda. for a gamma distribution. Alpha by lambda equal to 10 and alpha by lambda square equal to 25 because variance is alpha by lambda square. So when I substitute this alpha by lambda, I can substitute. So 10 by lambda equal to 25. So based on this, I am getting lambda equal to 0.4. If I get lambda is 0.4, alpha is coming out to 4. So this is becoming a gamma 4 comma 2.5 distribution. So any method of moments kind of an estimation is straightforward like that, right? But in some cases, it is even better to go with a maximum likelihood based estimation rather than a method of moment. Sometimes what you see is using this maximum likelihood estimation, probably the marks could be slightly higher, especially he gives a different kind of data set, and there is a possibility that the number of marks for a maximum likelihood kind of an estimation is slightly higher, because the way you frame the problem is slightly different for a maximum likelihood estimation. What it says is you first define what is called as a likelihood function. Likelihood function is nothing but you define the probability density function of that. Let's say the same example. The easier scenarios again would be, let's say we are talking of that exponential distribution, right? So for an exponential distribution, we know that the value, the likelihood function or the probability density function is lambda e power minus lambda x, right? You define the maximum. See, basically the difference between the two methods is, what the method of moment is going ahead with is, you just find out the average and the variance and use that for your estimation and probability purposes. What the maximum likelihood approach is saying is not just the average and the variance, because the data could be completely different, right? So what it is saying is you try to fit in this distribution for each and every value, not just on the average and the variance kind of computation. You try to fit in this distribution to each and every record. Now if you had 7 records here, right, in this example you had 6 records. See, what we have done, that 6 we have taken an average and we have found out that this is the value of lambda. But the method of maximum likelihood estimation, what it is saying is, that is not the aspect which we are looking at. You go with fitting it to each and every value. So you define this as, you define lambda into e power minus lambda x for each of the values, right? That is what we are calling as a first of all, likelihood function, wherein for each of the function we are taking the probability density function of the samples and we are doing a multiplication of all of them. So for let's say we have 6 examples, 6 samples are there. So 6 times we will multiply lambda e power minus lambda x, right? So 6 times we will multiply lambda e power minus lambda x. So basically x is nothing but the values which we got from the sample, right? So we will multiply it as lambda e power minus lambda. Like in our first data it is 14.84. This is my first observation, right? Similarly, you multiply it with lambda e to the power of minus lambda. The second observation is 0.19. Like that, you are multiplying all the 6 observations. See, here we are fitting. See, it's basically like each and every value which is there in your sample, you are fitting it. You are taking these as x. You are taking these values are as x, and you define the function. So basically, you are saying it as lambda e to the power of minus lambda 14.84 into lambda e to the power of minus lambda into 0.19 plus lambda e to the power of minus lambda into 11.75 and so on. This is, sorry, multiplication. So this is the first step we do. So which means we are involving all the values, right? And whatever is the product, we will find out the maximum value of this product. What value of lambda will maximize this product? That is why we call it as maximum likelihood. The likelihood is nothing but what distribution it is going to follow. Right? If it is going to follow a exponential kind of a distribution, for each one of them we are fitting an exponential distribution. And we are trying to maximize the product. So find the value of lambda in such a way that this product is completely maximized. Now, in this, the difficulty always is, in a multiplication, finding the lambda value which maximizes is a very difficult step. That is where people have come out with a small variation of that, which is log likelihood. You take the logarithm of all this instead of keeping them in the multiplication form. If you take the logarithm, it gets translated into an addition form. Right? The multiplication form, when you take the logarithm, log AB is nothing but log A plus log B. So log first number into second number will work out as log first number plus log second number. So because of that reason, that multiplication gets translated into addition, and after that you can do a maximization or a minimization. So basically it's like, if you see, the lambda is a constant. In this example, if I have to do that, so in this example itself, if I have to do that, see, we are saying that the probability is lambda e power minus lambda x. So if I am multiplying it, lambda 6 times I have to multiply. So probably this becomes lambda power 6 into e power minus lambda into x1 plus x2 plus so on up to x6. There are 6 numbers, right? E power minus lambda x1 into e power minus lambda x2, so on. It is becoming e power minus lambda into x1 plus x2 plus so on, right? So this is your likelihood function. Overall likelihood function is this one. Now what this method says is, find the log likelihood. This is the most commonly used tool across. It is saying find the log likelihood now. What is the log likelihood for me? Take the logarithm of this entire likelihood function. Right? Log lambda power 6, which is nothing but 6 log lambda minus lambda into the summation of x1 plus x2 plus so on x6. The summation we know, the summation value is 30.93. So we are saying 30.93. This is the log likelihood function. And now what it says is find the maximum value of this log likelihood function. How do I find out the maximum value of this log likelihood? We do it through differentiation. We take the derivative of this and equate it to 0. The derivative of any maximum value, to find out the maximum value of any expression, one common process we follow is we take the derivative of that expression and equate it to 0. So basically 6 log lambda, the differentiation is 1 by lambda. So 6 by lambda minus 30.93, lambda differentiation is 1, equal to 0. So from here it is coming out that the lambda is 30.93 divided by 6, which comes out to 5 point something. We have got, in this example, we have got it the same whether we have used the method of moments estimate or even the log likelihood kind of estimate. But what happens is, for a good number of data, using a log likelihood method of estimation is more comfortable. I mean, there are so many limitations associated with the method of moments kind of an estimate. Whereas the log likelihood method of estimate, probably for almost any parameter, you can easily compute, because as long as it is differentiable, we can compute the log likelihood estimate and find out the here we are not looking just at the average value. The only advantage that log likelihood estimate is bringing to us is we are not looking for only an average value kind of stuff. And even if there are multiple distribution, multiple data following multiple distribution, even just by taking a log likelihood, we can arrive at the values associated with them. Whereas in a method of moments, it's just that, okay, it is following one single distribution. Compound distributions and all cannot be handled effectively in case of method of moments estimation, whereas in log likelihood we can handle almost any of the steps. For simple things, both of them will give us the same kind of an estimate. So if I am estimating the parameter using this log likelihood function, maximizing of the log likelihood function, we are that is also estimating the parameters of the distribution. And once the parameter is estimated, probably the question could be on what is the probability something is more than this, something is less than this kind of stuff. We need to find the differentiation. Okay, in that actually there is one more step. Once we do the differentiation, okay, we have done the differentiation. So lambda, so we have got the differentiation. Let's say log likelihood, we have got it as 6 log lambda minus 30.93. This is what we got as the log likelihood. And we have equated it to 0. Right? Probably 6 by lambda minus 30.93, we have equated it to 0. Based on this, we have got lambda equal to 5 point something. The only thing is, once I do a differentiation, it can give me either the maximum value or minimum value. One of the two it can give me. See, once I have taken the differentiation, equated it to 0, this value lambda equal to something, whatever I am getting, it could be either a maximum value or a minimum value. To check out whether it is a maximum or a minimum, we again do the derivative of this once again. We take the second derivative of this. So which comes out to minus 6 by lambda square. right? And for this, anyhow, it's a constant, so differentiation is 0. So the second derivative is minus 6 by lambda square. And this is the negative value. Lambda square is positive. So minus 6 by lambda square is negative itself. So if this comes out to negative, we say that that value is maximum. If this comes out to positive, we say it is minimum. Because the differentiation and equating it to 0 always gives either a maximum or a minimum value only, nothing else. So I have to really check whether it is maximum or minimum. That checking can be done by taking the second differentiation and just seeing if that value is negative or positive. If it is negative, it's a maximum value. If it is positive, it's a negative value. It's a minimum value. Right? So generally, even if we don't do it, we'll always get that as a maximum itself. But just as a verification, we have to do this process, because probably he may have a mark or so for this kind of, are you checking whether it is really the maximum or not? For those kind of small things, there could be a number that could be given for that, a mark or two for that kind of process also. So if we see a random sample of size n is taken from a Poisson distribution, find the maximum likelihood estimator of mu. So here also, it's a Poisson distribution. So you have to be slightly comfortable there. So for a Poisson distribution, what is the function? Lambda per x e power minus lambda by x factorial, right? Now if I am talking about the maximum likelihood estimator in this case, I have to typically multiply it something like this. So this is lambda power x1, this is lambda power x2 into e power minus lambda by x2 factorial, something like that is coming up. Now if I am doing the multiplication of all these, it is coming out to e power minus n lambda numerator, because e power minus lambda is multiplied n number of times. So e power minus n lambda into lambda power x1 plus x2 plus so on, right? And divided by, this is anyhow x1, x2, x3, they are all constants, right? Lambda is what I need to estimate. I know the values of x1, x2, x3. They are all constants. So probably I'll simply write it as constant, nothing else. So now I will take the log likelihood function. What is log likelihood here for me? Minus n lambda, taking the logarithm of this, plus the log of lambda power x1 x2, which is nothing but sigma xi into lambda into x1 plus x2 plus x3, so on, and minus log constant, whatever it is. This is my log likelihood function. Now this log likelihood function, I will equate it to 0. So I am equating it to 0. So I have to take the derivative first of all. Derivative and equate it to 0. So which is becoming minus n. So this is log lambda plus sigma xi by lambda, and for derivative of a constant is 0. So this I am equating it to 0. So which is coming out that sigma xi by lambda equal to n. Based on this, it is coming out that lambda is nothing but sigma xi by n. So even without knowing what is the mean, I am able to find out the mean. We got the mean. Mean for a Poisson distribution is lambda. We can get it through this also. This is also saying this is nothing but mean, right? Sigma xi by n is nothing but the mean. Sum of the numbers by the total number of numbers. That's the mean. And mean is equal to lambda. Without knowing that mean is equal to lambda, we can even derive that using the method of moments kind of an estimate. So see, what typically happens is finding out this particular kind of distribution, finding out the parameters associated with each of these based on the sample data. Let's say I have collected some 50 sample data, and based on that I want to find out what is the value of lambda, right? So maximum likelihood estimation is what that can give us. And even in this case, if you are trying out the next differentiation, it is nothing but, so for this it is constant, and for this it is coming out to minus sigma I by lambda square, sigma xi by lambda square. So which is again a negative value. If it is a negative value, we are saying it's a maximum. If the second derivative is coming out to negative, we are saying there is a maximum value. Otherwise, we are saying there is a minimum value associated with the derivative, right? So the maximum likelihood estimation is much more, probably from an exam standpoint also, there could be a couple of questions that could revolve around the maximum likelihood estimation mechanism. So even in two parameters case, it becomes even more tougher. Let's say for a normal distribution, I have to do it, right? Okay. We know that the normal distribution, the PDF, the probability density function for a normal distribution is root 2 pi sigma square into e to the power of minus half x minus mu by sigma whole square. This is the probability density function that is associated with a normal distribution. Now he is asking me to find out the mu and sigma based on the sample observations, right? Now how do I find out the maximum likelihood? I have to multiply this n number of times. So when I am multiplying it, obviously I don't need to multiply this. This is a constant, right? 1 by root 2 pi is a constant. So probably it comes out like 1 by sigma, 1 by root of sigma squared is multiplied n times. So this will become 1 by sigma power n. And what about this part? E power minus half into x minus mu whole squared by sigma squared. So again the numerators will be added up, right? I mean the powers will be added up. So it becomes e power minus half sigma squared into xi minus mu whole squared. This is a sigma of that. I can write it like this when I am multiplying all this. So what will happen to my log likelihood? This is my likelihood function, multiplying all the individual probability density functions. And so from here, when I am taking the logarithm, log this, so it comes out as minus n log sigma minus half sigma square into the summation of xi minus mu whole square. This is what is my log likelihood function, right? Now I have to find out mu as well as sigma square, right? So what it is saying is, so here also, yeah, I need to find out the mu as well as the sigma square. So what it is saying, take the derivative of this. This is my log likelihood function. Take the derivative of this first with respect to mu, then with respect to sigma. Equate both of them to 0. So if I take it with respect to mu, this is a constant. So the derivative of this is 0. And coming to this, right? Coming to this, it is, how is this coming out? It is coming out as 1 by 2 sigma squared is constant, right? Minus 1 by 2 sigma squared is constant. And the derivative of this is nothing but sigma 2 into xi minus mu. The derivative of xi minus mu whole squared is coming out to 2 into xi minus mu. And again the mu derivative is minus 1. So which is coming out as sigma xi minus mu into minus 1 by sigma squared is equal to 0. Correct? I am taking the derivative and equating it to 0, which is nothing but coming out as sigma xi minus mu is equal to 0, and which is coming out as mu is nothing but your sigma xi. And okay, you are multiplying this to the power n, right? This sigma squared is getting multiplied to the power n. So mu is coming out as sigma xi in this case. Now same way you are doing the differentiation with respect to sigma. Now the same thing, if you differentiate with respect to sigma, what is that you are getting? Minus n by sigma minus, now this entire thing is a constant, xi minus mu whole squared is a constant, and this we are, and 1 by 2 sigma squared, the derivative of this is minus 2 by sigma cube. 1 by 2 sigma squared, the derivative is minus 2 sigma cube. So this is what again is coming out as your the derivative with respect to sigma. Here what we are talking of is, if there are two parameters, we will do it as a partial derivative. Right? We'll do a partial derivative, not a complete, which means we will, if I am differentiating it with respect to mu, I will assume sigma is constant. If I differentiate it with respect to sigma, I will assume mu is constant. Right? So straightforward. I mean, we don't need to look at it too much in this. See here, all we are saying is the likelihood function is 1 by root 2 pi sigma e power, or probably put it as 1 by root 2 pi, instead of sigma directly take it as sigma squared, variance. Inside the root you take the variance, easier to do. E power minus half x minus mu whole squared by variance, sigma squared. This is the typical probability density function of a normal distribution. Now assume that you are multiplying it n times. If you are multiplying it n times, what is happening? It is becoming 1 by root 2 pi variance to the power n. Right? You are multiplying it n times, so it is becoming to the power n. And what about this numerator? Minus half by variance into, the numerators will get added up. x1 minus mu whole squared plus x2 minus mu whole squared plus x3 minus mu whole squared is what it becomes. So all we are saying is sigma xi minus mu whole squared. That is the numerator. That is the equation for the likelihood. Now all I am saying is take the logarithm of this to make this log likelihood. Right? So the logarithm of this is log this one. Log 1 by root 2 pi variance to the power n plus log this one. The log this one is nothing but minus 1 by 2v into sigma xi minus mu whole square. That is the logarithm of that. So even this one, you can very well write it probably log, you split it. You split this as 1 by root 2 pi to the power n plus log 1 by root v to the power n and minus 1 by 2v sigma xi minus mu whole square. Right? So this is like a constant for you. Log 1 by root 2 pi to the power n is a constant. So you don't need to bother about it. And whereas this part, log 1 by root v to the power n. Root v I can write it as v power minus half. So v power minus half to the power n minus n by 2. Right? So log 1 by root v, I'll write it as v power minus half n. So it is coming out as minus n by 2 log v, correct? Minus 1 by 2v into sigma xi minus mu whole square. This is what is the log likelihood function. Now all I am saying is, you have to equate, you have to take the derivative of this and equate it to 0. But because we have two variables here, mu as well as sigma, two parameters are there. In our earlier examples of Poisson or exponential, we had only one variable or one parameter. So we were differentiating it with respect to that parameter and equating it to 0. Whereas because here we have two, which is mu, v variance and mu. Both of them are there. So what we are saying is, we are taking a partial derivative here, which is actually called as dou by dou x. We don't call it as d by dx. We represent it as dou by dou x. So dou by dou mu, dou by dou v. There are, so which means whenever I am differentiating it with respect to mu, variance will be treated as constant. So if I have to differentiate this with respect to mu, variance is treated as constant. So this is constant, right? So the variance is completely treated as a constant for us. And so the entire element is a constant here for us. Whereas the right hand side, it is coming out, if I am doing it as sigma x, so in the right hand side, 1 by 2v or probably minus 1 by 2v xi minus mu whole square. I have to take the derivative of sigma xi minus mu whole square. So it's like x1 minus mu whole squared plus x2 minus mu whole squared plus x3 minus mu whole squared. You take the derivative of that entire aspect. Right? So xi minus mu whole squared, if I am taking the derivative, it is nothing but 2 into xi minus mu. X squared derivative is 2x. So we are writing it as 2 into sigma xi minus mu. And mu I have to take a derivative again, which is making it minus. So this is what we are equating it to 0. So what is that it is saying? 1 by v sigma xi minus mu is equal to 0. Right? So it is coming out like sigma xi minus mu equal to, so if I'm expanding it, sigma of xi minus mu equal to 0. So which is nothing but x1 plus x2 plus x3 so on xn minus mu minus mu minus mu so on n times equal to 0. Right? So n mu, this is n mu. So n mu equal to x1 plus x2 plus x3 plus so on xn. So from here I can find out that mu is nothing but the sum of all these things divided by n. Sigma xi by n is what is the value of mu. Now the same logic I can go for estimating the variance also, because my log likelihood has come out as minus n by 2 log v minus 1 by 2v sigma xi minus mu whole square. So this I will differentiate now with respect to v, not with respect to mu. So my equation is minus n by 2 log v minus 1 by 2v sigma xi minus mu whole square. This if I am differentiating it with respect to v. So the left hand side, the first one becomes minus n by 2 into 1 by v. Right? And so here this part is constant, sigma x, because I will take mu as constant. Sigma xi minus mu whole square. This entire thing is constant into 1 by 2v. So 1 by 2 also I will take out as constant into 1 by v. The differentiation of 1 by v is minus 1 by v squared. Right? This I will equate it to 0. So what is that coming out? Here there are two minuses, so I can take that out. Sigma xi minus mu whole squared into 1 by 2v squared, right, is equal to n by 2v. Correct? I am taking n by 2v to the other side. So basically if I am looking at cutting it off, 2 I can strike off, 1v also I can strike off. So v is coming out like sigma xi minus mu whole squared by n. So v is nothing but the variance. The estimation of the variance in this case is coming out as sigma xi minus mu whole squared by n in case of normal distribution. So mu we already have found out what is that mu. Sigma xi by n is what we have called as mu. So substitute that sigma xi by n in case of mu, that is what it is coming out as the variance for the distribution. Right? So, I mean, what we are trying to drive is, if at all we don't know the distribution if at all we don't know the parameters of the distribution, we can use this kind of maximum likelihood estimator or the method of moments kind of an estimator to find out those parameters. Whatever are the distribution, you can use the method of moments or method of maximum likelihood kind of an estimator to find the values of the parameters. And once you found the values of the parameters, you can use it for doing any kind of calculation. And probably in the next couple of things, we will also see that if there are some incomplete values, right, not too much of data available, or truncated values, only some portions of the data available, some portions not available. Even in those cases, the method of maximum likelihood estimator can help us in estimating the parameters. So those are some of the major applications associated with the method of maximum likelihood kind of estimation.